Hi, and thanks for tuning in. My name is Sebastian Popescu, and today I'll be presenting our paper on distributional Gaussian process layers for outlier detection in image segmentation. Right. So, what are we going to talk about today? We're going to start with a brief introduction to outer distribution detection and what it means to be an outer distribution example, and we're going to see some drawbacks of using neural net-based methods for outer distribution detection. Then we're going to propose using Gaussian processes instead and see what are some challenges in using them. More precisely, how to sparsify them, how to extend them to deep architectures, and whether they are suitable for outer distribution. Afterwards, we propose a new type of GP and see how to devise a drop-in replacement for convolutional layers using the aforementioned. Finally, we introduce some applications of this newly introduced module on outer distribution detection on brain MRI scans. Right. So let's dive straight into it. If you look on the left-hand side, you will see the data manifold with three different classes. We see the training points, the testing points, which are still inside the data manifold. We also notice adversarial examples at the boundaries, whereas the outer distribution examples sit outside the manifold, and they can be categorized into novel examples or outer distribution examples, as you can see on the right-hand side with some examples. In this talk, we will refer strictly to outer distribution examples, even though our model is capable of also detecting novelty examples. All right. So we now turn our attention to how outer distribution examples can make their way in medical imaging. For example, on the left-hand side, you see an ROI segmentation algorithm which was trained on healthy brains, but is now applied to a post-operative MRI scan, which is clearly outer distribution in this context. We essentially want reliable uncertainty quantification in the abnormal regions affected by surgery and TBI. On the right-hand side, CT scans can have artifacts, and I think we can all agree that we want an algorithm that can detect that something fishy has happened in the reconstruction, such as having a gorilla in your lung, as in this silly example over here. How can we detect outer distribution examples using machine learning models? In this case, we have three commonly used algorithms for outer distribution detection, such as deep ensembles, MC dropout, and just using a GP on top of a neural net architecture. So we have two different toy classification data sets with the two classes given by the orange and blue points, and a set of outer distribution red points, which we want to highlight. With brighter colors, we denote regions of high uncertainty as given by each model. From all examples, we can observe that high uncertainty is usually allocated tangential and closely parallel to the decision boundaries, and that in no occasion does the model highlight the red points. This is problematic, and for this reason, we are going to ask ourselves, what should we actually use then? And my answer is Gaussian processes, which are a non-parametric learning model, which basically assigns a multivariate normal distribution over the values of the data, on top adding a likelihood to obtain the observation model. On the right-hand side, we can see that if we constrain on the training points, we can obtain a posterior at unseen points that has a mean and a variance with higher variance values when you go further away from training points. This property makes GPs ideal for outer distribution detection. Right. So after introducing the basics, we can ask ourselves if we can do outer distribution with GPs in practice. And the answer is yes. Looking at the previously introduced toy data sets, with brighter colors, we have higher variance, and we notice that the red points are correctly identified as outliers. So now you might be wondering, why can't we just use GPs on everything? So there are some problems with GPs, namely that both during training and at testing time, we have to invert an n by n matrix, where n is the number of training points, which quickly gets unfeasible for even medium-sized data sets. Hence, we need to sparsify our inference framework for GPs. Secondly, we would like something that can model complex and non-stationary signals, which with a shallow GP, you just can't. Hence, we would like to stack GPs on top of each other to replicate a neural network architecture. Thirdly, a quick question is whether this stacked GPs still have the same auto-distribution capabilities as its shallow counterparts, and if not, what can we do about it? And finally, because of the curse of dimensionality, using a straightforward kernel wouldn't quite work for high-dimensional data sets such as images or 3D medical scans. And for each of these points, we are going to see in the upcoming slides how to solve them individually. Yes. So addressing the first problem, namely how to sparsify the GP, we can take a variational inference approach. So instead of having all the training points, we can introduce this artificial set of data points called inducing points, which are tasked to emulate the properties of the entire training set, but with a significantly lower number of data points. So we can look on the right-hand side, upper row, with yellow stars, you have the location of the inducing points, and we can see that the predictive mean, also variance of the upper row, is similar to the ones from the bottom row, which stem from a full GP. Hence, the 16 inducing points are just as good at as the over 1,000 training set points, since they arrive at the same decisions, essentially. All right, so moving on. So the question now is, what type of uncertainties do we need in machine learning models, and especially in ones which are applied to medical imaging, where the cost of making mistakes is quite high? So in Bayesian neural nets, the observation model is composed of integral over the weights distributions and epsilon, which is just the added observation noise. By simple maths, we can decompose the total uncertainty into two components. The model or epistemic uncertainty, which is essentially the uncertainty in the weights of the neural net, and aleatoric uncertainty, which is just the variance of epsilon. So what do this actually capture? If we look at the figure on the left-hand side, we can see that the epistemic uncertainty grows away from the data, such as is the gap between the two clusters of training points. And on the right-hand side, in a classification task, aleatoric uncertainty is present in regions of input space where there is an overlap between data labels. All right, so these are the two types of uncertainties you can gain with Bayesian neural nets. Now, the natural question is, what type of uncertainties can you obtain with sparse variational GPs? So the cool thing about the GPs is that you can actually write down the posterior equations in closed form, meaning that you can actually integrate the variational posteriors out. If we look at the variance, we now have three types of uncertainty. We still have the aleatoric uncertainty with the same properties as before, but now we can split epistemic uncertainty or model uncertainty into two constituent parts. Within data uncertainty, respectively, distributional uncertainty. If we look at the figures, we can easily spot the conceptual difference between them, namely that within data uncertainty is tasked to cover the spread of output values after subtracting homoscedastic aleatoric uncertainty. This is in a regression setting, whereas for distributional uncertainty, it is high outside of the data manifold, hence we can use it as a measure of auto-distribution detection. Yes. So addressing the third problem in our series, so with this under our belt, we can progress towards the next problem, namely how to create hierarchical architectures with sparse GPs. Essentially, deep GPs can be visualized on the right-hand side. You can just imagine the architecture of a neural net, and instead of having weight matrices, you can essentially replace the column weights of these matrices with sparse GPs. And the advantage of deep GPs is, if you look on the lower row, it is more capable of modeling non-stationary signals as opposed to a GP. Right. So now the question is, if this hierarchical architecture composed of sparse variational GPs, if they are still suitable for auto-distribution detection, just as shallow GPs. And unfortunately, the answer is no. As you can see in the figure here, we have a three-layered deep GP where we have plotted just the distributional uncertainty with the x-axis being our input space. And we essentially have training data between -5 and 5. In a hypothetical scenario, we want what is less than -5 or bigger than 5 to be detected as an outlier, meaning high distributional uncertainty at each layer. What essentially happens is that in layer 2 and especially in layer 3, we have a pathology that what was initially in layer 1 detected as an outlier is now an inlier. We can see that as we increase the number of inducing points, this pathology only gets worse, which is something that we obviously don't want. So how can we solve this problem? For the hidden layers of the deep GP, we can introduce this hybrid kernel, which is essentially the Hadamard product between standard Euclidean space kernel and a kernel with Wasserstein 2 distances between the Gaussian measures stemming from the previous GP layer. Because if you remember, for any data point, a GP returns a Gaussian distribution. We have an analytic formula for the Wasserstein 2 distance between multivariate normals, which is good. And in this kernel formulation, our inducing points are no longer in the Euclidean space, so they are not scalars anymore, but they actually follow a multivariate normal distribution now, because each inducing point location denoted by Z needs a mean and a variance for the hybrid kernel. We can see the motivation behind this in the figure over here. If you look on the left-hand side, that would correspond to the typical deep GP case where we just use Euclidean kernels. We have with green the inducing point, with blue an inlier point, and with orange an outlier point. The lines denote the PDFs of the aforementioned points, and with dots we denote samples. As we can see, the 2 points are equidistantly placed with respect to the inducing point sample. So if you actually calculate the distributional variance, you get the same value. So what was initially an outlier will now have the same distributional uncertainty as an inlier, which is something we don't want, obviously. Now, looking on the right-hand side at the hybrid kernel, because we now take into consideration the Wasserstein 2 distance between their actual PDFs and not just samples, we can notice that the distance between the green and orange PDFs is much higher than the distance between the green and blue PDFs. Hence, the distributional uncertainty of the outlier will remain high going forward to the next hidden layer. All right, so this was the conceptual difference between deep GPs and distributional deep GPs. And now the question boils to whether these things are actually suitable for auto-distribution detection. We again have a 3-layered deep GP in the top row and a 3-layered distributional deep GP in the bottom row. If we look at the columns entitled distributional variance, which, as you might recall, is a measure of auto-distribution detection, we can see that in the second and in the third layer, the distributional deep GP does a better job at highlighting points which are outside the data manifold as opposed to the deep GP, which extrapolates quite widely and incorrectly regions with low distributional variance. So, question, are we there yet? Can we use now what we have learned so far and apply it to image data or 3D medical scans? And the answer is no, not yet, because we still suffer from the curse of dimensionality. Hence, we need a specific architecture to work well in high-dimensional settings. And this is, incidentally, the main point of our paper. So this is essentially a new module which we have introduced, which can act as a drop-in replacement for usual convolutional layers. So what essentially happens is we have a 3D block of the brain, and we use a standard sparse GP and convolve it on the patches, denoted with orange in this figure, to arrive at the stochastic layer denoted F1. Now, the difference is that in this stochastic layer, each cell has a Gaussian measure as opposed to just a scalar as in usual conv nets. Now we apply an affine operator, which is denoted by green in the figure, which acts as a replacement for the standard filter convolved. But at the end, we still obtain a stochastic layer denoted by F2 pre-activation. And as the name says it, we now need an activation function. So unlike usual activation function used in neural nets, we don't use ReLU or sigmoids, but instead use a distributional GP denoted as light brown in the figure in a one-to-one manner to act as a non-parametric activation function that correctly propagates uncertainty forward. All right, so what are some properties of this module? In previous research delving into auto-distribution detection in neural networks, they basically showed that it is desirable to have an upper bound on a function, say a dense layer for neural networks, so that what was initially closed in lower layers will still be closed going forward. This is a desirable property for auto-distribution detection. And the good thing about our module and working in Wassestein 2 space is that you can calculate this Lipschitz constants explicitly for both the affine operator and this distributional GP activation function. And you have here the results essentially. Right. So what we want is for objects which were closed in previous layers to still be closed in forward layers, and we can impose a non-expansive map, which essentially means having a Lipschitz constant equal to 1 to the affine operator by redefining it in the way which you can see in this slide. All right, so you might be wondering what effect this has in practice. In the upper row, we have the unconstrained version, and in the bottom row, the Lipschitz constrained version. If we look at the distributional variance for each layer, the Lipschitz one does a better job of reducing the variance inside the data manifold as opposed to the unconstrained one. So this will be helpful for auto-distribution detection. All right. So what is the actual architecture which we apply in our paper? We use a relatively simple one composed of two measure preserving this GP layers. And in output space, we get three heat maps, the mean segmentation and the two types of uncertainty. We compare our model with state-of-the-art methods from general auto-distribution literature, which is enumerated over there. All right, so what is the study design? We operate in a supervised learning scenario, so we need to learn what is normal inside the brain. For this, we use the UK Biobank and T2 FLAIR scans with a proxy task of brain tissue segmentation. Then, going forward, we use BRATS, which, as you all know, has scans with tumors, which under this context can be seen as outliers, given that the UK Biobank doesn't have any. Bottom line, we essentially want to detect the tumors as outliers. So how do we do this? If you look at if you look at the histogram over there, we have the distributional variance histogram for all the voxels part of the UK Biobank, where we operate under the assumption that every voxel is an inlier. We set the threshold for what an outlier is at the 5% false positive ratio. Whatever is beyond this threshold, we set it as an outlier in the BRATS scans. And then we compute the die-score with respect to the ground truth tumor segmentations. So what are the results? In terms of brain tissue segmentation, our model is quite competitive with a standard unit, which is quite impressive as the unit has many more layers and larger field of view for each voxel, alongside a significantly higher number of parameters. This is essentially a testimony towards the non-parametric representation capacity of those distributional GP layers. So in terms of outlier detection, our method is able to outperform all the other baselines by quite a bit. And how do the results actually look like visually? If you look at the last four columns, we can see the tissues above the threshold set at four different false positive ratios. We can see that our method, which is the first two rows, it performs quite well on the two scans, whereas also OVADM, which is the last two rows, also does a reasonable job. Okay. So to wrap things up, we created a drop-in replacement for convolutional layers, which is capable of correctly propagating uncertainty forward. We have shown that our architecture, which is quite small, is almost as good as a standard unit in terms of segmentation, whereas in terms of outlier detection, we managed to beat both supervised and unsupervised methods present in literature. All right. So what do we still need to work on this project? We still have to look at the function space properties, both in prior and posterior space, so we can get some theoretical intuitions as to what these models are able to represent. We would also like to scale our module to larger architectures such as UNet, ResNet, or a Vision transformer. And one drawback of this module is the increased training and testing time speed due to matrix inversion. So in the future, we would like to implement the matrix inversion-free inference scheme for our model. And last but not least, we would also like to expand our study into other tasks and modalities in medical imaging.